cross product. Okay, cross product between any two vectors. Okay, cross product between any two vector A cross B, isn't it? We write like this: A is a vector, B is a vector, A cross B. That's equal to magnitude A, magnitude B into sine of angle between A and B, not over. It's a vector. Okay, cross product is a vector. We put a unit vector n cap. We say this n cap, this cross product, this n cap, okay, cross product direction, which is perpendicular to both A and B. Okay, and that direction is very important. Okay, so A cross B, that is defined as magnitude A, magnitude B, sine of the angle between them, okay, into n cap, where n cap is perpendicular to both vector A and vector B. Is that okay, this symbol? If I write like this, is that okay for you? Perpendicular to. Is that okay? And one more thing, you were to directly take A cross B is equal to minus B cross A. Magnitudes are same, but direction is opposite. Okay, you were to take these two in the beginning. Is that okay? A cross B is equal to minus B cross A. Okay, now we shall see how to find this direction. I hope A, B, sine theta, you know all of this. Okay, we shall see how to find the direction of the cross product, which is very, very important. Okay, because our magnetic force is a cross product, isn't it? In case of your Biot-Savart's law, cross product will come, isn't it? In many cases, we will end up with a cross product, and cross product direction is very important. Okay, now let me again, whenever you have two vectors, okay, can you grab me that one, that red one? Yeah, is that okay? So suppose you have two vectors. Okay, you have two vectors in space. Can you see this one? You have two vectors in space. Yes, now whatever the orientation or something of the vectors, okay, you can construct a plane containing those two vectors. Okay, you can always construct a plane containing those two vectors. Can you see this one? Suppose you have vector like this, you can construct a plane like this. You have vector like this, you can construct a plane like this, isn't it? Suppose vectors are like this, you can construct a plane like this. Is that okay? So whatever the whatever you do, okay, whatever the manipulation you do, you can construct a plane containing these two vectors. Is that okay? Can you imagine this one? Okay, so if you have any two vectors, okay, you can always construct a plane containing those two vectors. Is that okay? So now let me take a plane here. Can you imagine? Kind of horizontal pitch. Wait a second, I need that one. Is that okay? Horizontal plane. Is that okay? You have this one, okay? There's nothing big deal, okay? Now let me take two vectors first, okay? Then later let me construct a plane. But I am drawing first plane, then vectors, okay? You first draw the vectors, then construct a plane containing those two vectors. That is what we usually do, okay? But while drawing, this is more comfortable, okay? Let me take this one as vector B, okay? Vector B. Let me take this one as vector A. Okay, there are two vectors which are drawn like this, whose tails are coincided here, okay? Those two vectors on this plane, whatever I have drawn. Can you imagine this one? Now, suppose this is the angle between them. Theta is the angle between them, okay? Theta is the angle between them, okay? These are the vector on a plane like this, okay? Like what I have shown, okay? These are the vector like this. That okay? A vector, B vector like this. There are some angle. Is that okay? Yes. Now look at here. Again, magnitude A, magnitude B into sine theta. What is the n cap direction? Okay, what is n cap? Again, I told n cap is perpendicular to both A and B. Obviously, that n cap is perpendicular to this plane, isn't it? Okay. If you draw any line perpendicular to this plane, that is perpendicular to both A and both B, isn't it? Suppose if you take two vectors here, okay, if you take two vectors here, if you draw any what you call perpendicular here, that perpendicular, I mean, if you draw any perpendicular to the plane, okay, that perpendicular is, that is perpendicular to both vectors, isn't it? So obviously that n cap should be perpendicular to the plane. That's what you can see here, isn't it? N cap is perpendicular to the plane. But so there are two perpendiculars to the plane, isn't it? One is like this, other one is like this, isn't it? What is the direction of n cap? Isn't it? Again, I told n cap is perpendicular to both A and B, but there are two perpendiculars like this, in this direction and in this direction, am I right? For a plane. One is opposite to other, isn't it? Now, which one of these? Okay. So now, for that, you need to use either screw rule or right hand thumb rule. Okay. Let me first use right hand thumb rule. Right hand thumb rule says, okay, so direction of A cross B should be taken like this, okay? A cross B, am I right? A and B. A comes first, B later, isn't it? A cross B is minus of B cross A, okay? Once you find A cross B, you can find B cross A, okay? Now, so if you want to find direction of A cross B, okay? So you just rotate your fingers from A to B. You just curve your fingers from A to B. A to B, not B to A, okay? A to B, okay? And your thumb will represent the direction of cross product. Okay? Your thumb will represent the direction of cross product. This is A cross B direction or n cap direction. Is that okay? And that is obviously perpendicular to the plane. Is that okay? Now, if you want to find B cross A, okay? So you have to curve your finger from B to A, okay? From B to A, okay? From B to A. So then thumb will represent the direction of, speak out. So cross product. So can I just draw it like this? This is B cross A. Is that okay? That's one idea, right hand thumb rule. Wait a second. So other idea is screw rule. Screw rule means, I mean, you should have some experience with nut and bolt actually. Is that okay? Whenever you rotate nut like this, okay, nut or bolt like this, okay, it will go above. I don't have any nut and bolt here, isn't it? So again, it will go up here actually. Suppose if you have a nut here, if you have a bolt here, if you rotate bolt like this, this bolt will go up actually. If you have that experience, then only use screw rule. So it will go like this, isn't it? So like that, A to B, A cross B, you can take it like this. If you have experience with nut and bolt, then only use screw rule. Otherwise, use right hand thumb rule. That's the best idea. Is that right hand, not left hand? If you are left hand, you will be in trouble. Wait a second. Is that okay? If you rotate a screw from A to B, look at here, that screw will go like this actually. If you rotate again, so that's why A cross B is given by the direction of the motion of the screw. If you rotate A to B, it will go like this. You can imagine like this, okay? B cross A, just again B to A, am I right? B to A. So just rotate screw like this, it will go down actually. Is that okay? If you have a bolt here, it will go down actually. Okay? If you have any nut and bolt nearby you, just try this one. Okay? So that's another idea. Screw rule. But I will use a thumb rule. That's the best idea. Okay. Sometimes I use screw rule. Okay. Most of the case I use screw rule. But if you don't have any experience with nut, bolt or something, okay, use thumb rule. Okay. A to B, thumb will represent the cross product direction. Suppose if you need B cross A, so B to A, your fingers, your four fingers, they should go from B to A. They should curve from B to A. So then your thumb will represent B cross A. Obviously, you can see B cross A is negative of A cross B, isn't it? Yes. And their magnitudes are same actually, but direction is opposite. Yeah, speak out.
Sir, I was saying that we can use the bottle cap also, sir, for understanding, sir. Bottle cap.
Bottle cap. Yeah, that's the best idea, isn't it? Bottle cap, isn't it? A to B, am I right? A to B, it will go up actually, isn't it? Yeah, bottle, most of you have used bottle, isn't it? That's the best idea, okay? Most of you have used bottle, isn't it? I will rotate from A to B, okay? I'll start from A, I'll rotate from A to B. It will go up. No, I'm not using any thumb rule. Okay, I'm rotating this one. Look at here. I'm just rotating from A to B. A to B. It is going up. Am I right? It is getting open here, isn't it? If I rotate from B to A, okay, it is go down, isn't it? Yeah, I think you have used bottle cap. You can use screw rule. Okay, you can use screw rule definitely. Okay, or use right hand thumb rule. A to B thumb, B to A thumb, like this. Is that okay? And that cross product is perpendicular to the plane containing A and B. Okay, A and B need not be like this. A and B in any orientation. Okay, this A cross B is perpendicular to individual vector. It is perpendicular to the plane containing A and B. Is that okay? What are the examples? The best examples are your angular momentum. All right, R cross P. If you have a what you call particle, suppose let me take XY plane here. Okay, X axis here, Y axis here, Z axis here. Okay, that plane is XY plane. Suppose our particle is moving in a circular motion on XY plane. Particle of mass m which is moving in a XY plane in a circular motion. Okay, so then obviously you can draw that radial vector. This is origin. Okay, so this is R vector actually. Can you see this one? This is R vector. Usually this is P vector. Both R and P are on XY plane. Particle is constrained to move on XY plane. Okay, so then R cross P. What is R cross P direction? This is R vector direction. This is P vector direction. R cross P, that is perpendicular to that one. Okay, R and P are on XY plane. Okay, they are perpendicular actually. You can see, isn't it? If particle moves on a circle, R and P are what you call R vector. I mean radial vector from the origin, and its momentum or velocity, whatever you take. Okay, those are perpendicular actually. Okay, obviously this R cross P is what you call out of the plane, so we call it as angular momentum vector, isn't it? So similar to that one, we have one more example, torque. Am I right? Torque is equal to R cross F, isn't it? Torque is equal to R cross F. We write like this. That's also cross product, isn't it? Again, in our case, in our application, again we use this one. Okay, we use this one, this expression and all. So along with that one, in our application, most of the case you use this one. Your magnetic force on the charge, force on the moving charge due to magnetic field, that's equal to charge multiplied with cross product with velocity and magnetic field, isn't it? Lorentz force law. So we are going to apply our cross product here in many cases. Okay. Also we are going to apply our cross product in case of Biot-Savart law. Am I right? It also contains cross product, isn't it? Now again, so historically this cross product was, I think, invented to work out some geometry. Okay, just see Wikipedia or something about history. But now we have a lot of applications of this one. Okay, and so now try to answer one question here. Okay, why angular momentum should be perpendicular to these two? Why you define a quantity which is perpendicular to both of them? What is the significance of that direction? Okay, try to answer this question. Let me address this one in the next class. Is that okay? I mean, why cross product is written as a vector which is perpendicular to both vectors? Is that okay? No, that doesn't matter. That's a different story. If cross product vanishes, we can say they are coplanar like that. That's a different story. I'm saying why cross product is defined as a vector which is perpendicular to both vectors. Again, so they might have invented that one to work out some geometry or something, but we have application here. Okay, take one application, try to convince a point. Okay, what is the what is the importance of this direction? Is that okay? What is the importance of that direction? Let me give the hint. Yeah, speak out.
Sir, if we are taking the cross product and if we take that theta goes to 0, then it will not vanish. That's why.
Yeah, obviously, if theta equal to 0, it will vanish. Why not?
So
if charge move in the direction of magnetic field, it will not experience any force. Yeah, speak out.
Sir, I am saying if resultant is not perpendicular, sir, and sir, we are theta is 0, then it will not vanish, sir. That's why, sir.
Resultant is not.
Sir.
No. Again, so forget about scalar. Yeah, scalar is also important. Scalar part is very important. It depends on magnitude of A, it depends on magnitude of B, it depends on sign of the angle between them. That's what this force varies actually. This force varies as sign of angle between them. This force depends on magnitude of A. This force depends on magnitude of B. Is that okay? It depends on sign of the angle between them. Not only that, look at here. This force is in the direction of cross product. I mean direction which is perpendicular to both. Am I right? Here you can explain. Here you can explain why that one should be perpendicular to individual, isn't it? Because you can experience a force. You can see the motion of the charge here, isn't it? So again, in this case, how do you explain? Isn't it? So there will be always the question comes, okay, because we have taken this one as a definition. Am I right? The question comes, why, isn't it? In the definition, we don't question that one. Why? Isn't it? We take it as it is, then we apply, isn't it? Yes, I don't think you can explain why it should be perpendicular because it is defined like this here. But take on application and try to convince yourself that why the cross product is required to define as a vector and why it is required to define perpendicular to both. Obviously, in case of Lorentz force, it will be very clear, isn't it? So again, in case of angular momentum, how it is written? In case of torque, okay, R cross P. Sorry, R cross F, isn't it? In case of torque, why that cross product should be, why we should assign a direction to that one? Okay, what is the role of the direction? Let me give the small hint here. Wait a second. Let me give the small hint. You have a rigid body, okay? It is rotating like this, rotating about this axis. Am I right? Like this. Let me take anti-clockwise direction, okay? So this is rotating like this. Then its angular momentum will be in this direction. Can you imagine? L vector. And if the same rigid body, not same, different, okay? Yeah. If it rotates like this, then your angular momentum is like this. Am I right or not, anyone? Angular momentum. Am I right? Yeah. Or you take individual R cross P, you make the summation. Take individual small masses and take R cross P, you can make the summation. Is that okay? Now look at here. So this is opposite to this one. This is opposite to this one. That's why this vector contains the information that whether it is rotating clockwise or anti-clockwise. Isn't it? That vector direction will tell you whether it is rotating clockwise or anti-clockwise. That information is there in the cross product. Is there, that information. Look at here. How much angular momentum, that is magnitude, isn't it? Magnitude may be same in both cases. Suppose let me take omega same, okay? Let me take omega same. Magnitude may be same, okay? But there is one more information. This is also rotating, this is also rotating with same omega. But one more information is there. What is that information? This is rotating clockwise, this is rotating anti-clockwise. That information is there in the vector. Isn't it? So that's why the vector cross product is perpendicular to them, which will talk about, in this case, in these two cases, okay, it will talk about the whether it is rotating clockwise or anti-clockwise. Is that okay? Yes, speak up.
Is it linked with vectors and matrices, like rotation matrices?
No, not rotation matrices. Again, that's a different story. Rotation matrices, this is a rotation of a vector, transformation of a vector. That's a different story. I'm not talking about transformation of a vector. I'm talking about cross product between two vectors. Transformation is different. Okay? Yeah, speak out. You are asking some question?
No, sir. I am asking that for a cross product, it is a rotational motion and we require a axis.
Yeah.
Something
Cross product, I mean, these two, torque and force, that will talk about some rotational motion, am I right? So that rotational motion, that rotation should be with respect to some axis, isn't it?
Yes.
One thing, okay? And this vector is along that axis, look at here. This angular movement means along that axis actually, one thing. And other one is, you have one more information, whether it is clockwise rotation or anti-clockwise, am I right? That information also exists in the what you call cross product actually. I hope this convinces us why that cross product is needed to be defined as a vector. Okay, and what is the significance of that vector part? Is that okay? Yes. Now let me take some simple things here. Suppose if you have two vectors, okay. If both vector A, vector B, okay, if angle between them is 0, okay, or 180 degree, 0 or 180 degree, okay, if theta is equal to 0 degree or 180 degree, okay, then A cross B, speak out, what is this one? Sine 0 is 0, sine 180 is 0, am I right? It's equal to 0 into n cap, or it's a null vector. Is that okay? So that's why, as you told, cross product is a test of whether vectors are collinear or not. Isn't it? If cross product vanishes, vectors are collinear. We call this as collinear vector. Okay. If cross product is non-zero, okay, then vector are non-collinear. They have some angle between them. Is that okay? So thereby, cross product is a test of whether vectors are collinear or not. Okay. If vectors are collinear like this, A here, B here, or A here, B here, is that okay? B here, so theta equal to 0, theta equal to 180 degree here. In that case, cross product vanishes. Is that okay? Yeah, speak out. Now, so now again I can write one more thing, okay? A cross A, cross product with itself, that's a null vector, okay? Is that okay? A cross B, that's equal to null vector if theta is equal to 0 degree or 180 degree, isn't it? Where I have taken A and B are other than null vector, okay? But cross product vanishes if they are collinear, isn't it?
Sir,
Yeah.
sir, if I will change the origin
Hmm.
in the rotation,
Hmm.
will it change the direction?
We have to check out, okay? You are again talking about transformation of coordinates. It is there, okay? It is there in the next topic. In this vector analysis only, he gave the transformation of the coordinate and all. Yeah, your angular momentum vector, I think it changes, okay? It depends on coordinate. You have to write angular momentum with respect to some coordinate. Like that you need to write. Yeah, or just study some classical mechanics. I mean, I think if you see Daniel Kleppner book, okay? What is that title? Book title?
Are you saying momentum inertia?
Again, these are depending on the origin, that is worked out very nicely in Daniel Kleppner book. Just check that out.
Okay.
I mean, defining angular momentum with respect to different coordinates, isn't it? Just work that out. Yeah, speak out.
An introduction to mechanics.
Introduction to mechanics by Kleppner and Coleno. Okay, just see that one again. Whatever you are asking, that is worked out there. Okay, yeah, that's true. Okay, these vectors are defined with respect to some coordinate. Okay, if you change that one, that will change. That's correct. Is that okay? Now, one more distributive property. This is distributive. A cross B plus C, isn't it? That's equal to A cross B plus A cross C. I hope this is not a big deal for you, isn't it? Is that okay? Distributive property. One more thing. What is geometrically A cross B means? Okay, I mean, again, what is the geometrical meaning of mod of A cross B? What is this value actually? Mod of A cross B. Anyone quickly? You have vector A here. Let me take big diagram. Vector B here, okay? Now you can construct a again, these are on the plane of the board, okay? Is that okay? So these are on the plane of the board, okay? Let me take is that okay? Let me take it like this. This is theta. Is that okay? This is theta. Now look at here. What is this magnitude of A cross B? Can anyone tell me? What is the geometrical meaning of that one? What is the geometric? What does that value signifies? Quickly, anyone remember it? Area of the parallelogram whose sides are A and B, isn't it? Now look at here. So A cross B, again magnitude is means nothing but AB sine theta, am I right? With magnitude. See this sometimes theta, sine theta may give negative value, isn't it? Now what is this B sine theta? Check this out. B sine theta is this height, am I right? Check this out. This is B, so this is B sine theta. B sine theta, okay? B sine theta multiplied with A, height into this base kind of thing, am I right? That is actually area of the parallelogram. Area of the parallelogram. Area of the parallelogram generated by A and B. Is that okay? Magnitude of A cross B have got one geometrical significance. Okay, geometrically, magnitude of A cross B is the area of the parallelogram. Area of the parallelogram generated by A and B. Is that okay? Now look at here. This itself says if B coincides with A, okay, or if B is opposite to A, then what will happen? This area will become 0, isn't it? That means cross product vanishes. Magnitude is 0, isn't it? If theta equal to 0, then area will become 0. No, magnitude. I am talking about magnitude. Magnitude is scalar 0. Is that okay? If B is 180 degree, then in that case also this area is 0, isn't it? If A like this, if B is like this, okay, then there is no area, isn't it? Constructed by them, isn't it? Area of the parallelogram is 0, isn't it? That's how we can explain. Now, until now we have taken a kind vectors without any reference of coordinate system, am I right? We haven't taken any coordinate system, isn't it? Now we shall start taking one origin, one coordinate x, y, z like that. Is that okay? And we shall define vector using that one, okay? So now let me take a origin here. Let me draw axis here. There is a rule of drawing this axis, okay? Order is also very important, okay? This is x-axis, y-axis, z-axis. Can you imagine these two are perpendicular? Actually, I can't draw that one on the board, isn't it? Actually, I can't draw this as out of the board, isn't it? That's why I draw it like this. Is that okay? But these two are what you call perpendicular to each other. Is that okay? These two are perpendicular to each other. These two you can see, isn't it? Is that okay? X, Y, Z. This order also does matter. We shall see that one. X should be here. If X and Y are here, Z should be here. Okay? We shall see that one. That is decided by cross product again. Okay? So these are what you call orthogonal coordinate system, or you can say Euclidean coordinate or something, isn't it? Now what we do is we define a what you call unit vector along each, okay? we define a unit vector, x cap, y cap, and z cap. Okay, we call it as x cap, y cap, and z cap. Is that okay? Unit vector whose length equal to 1, direction along the respective axis. Is that okay? Now, if you want to represent any vector, okay, let me take x, y, z, x here, y here, z here, okay. Suppose let me take a vector from origin to some point, okay, and any vector A, okay, from origin to some point, okay. Where we wish to represent this vector using these unit vectors actually. We are going to write that vector A like this. A is equal to ax into x cap plus ay into y cap plus az into z cap. I think you got to write separately so that you can imagine that one. Ay into y cap, okay, ax into x cap, ay into y cap plus az into z cap. So what is that one? Look at here. Again, that means this is a kind of decomposition of a vector actually. You have to see this one as decomposition of a 3 vectors, ax into x cap. Suppose what you can do is you can draw the projection on this xy plane, okay? You can draw this projection of this vector A on xy plane, and then you can take this one, and then you can take the projection of this line on x-axis. Is that okay? Let me draw it like this. Is that okay? Can you imagine that one? So projection of this line on this axis. Is that okay? And we call this one as ax, ax into x cap. This one is ax into x cap. Ax into x cap. Is that okay? And if you draw the projection of this line on y-axis actually, let me take y-axis like this, okay? Like this approximately. This is a perpendicular, okay? This is a perpendicular, okay? So then this vector is actually what is this vector? Ay into y cap, okay? Now ax into x cap, ay into y cap, okay? If you add these two, what is this one? This is this resultant, am I right? Check this out. On xy plane. On xy plane, what is this one? Ax into x cap plus ay into y cap. If you add any two vector on xy plane, you will get a vector on xy plane, isn't it? And one more, what I do is I am going to draw up what you call perpendicular to z axis. Can you imagine that one? I am going to draw perpendicular to z axis. This is a perpendicular, okay? So then I am going to define a vector. Wait a second. These should be drawn very clearly. Then you can imagine. No, that will not work in that video actually. Only we can see that one. Am I right? Is that okay? Still, again, these two should be similar actually. Okay. Is that okay? I have drawn a perpendicular to z axis. Okay. So then let me define this vector as az into z cap. Okay. Now look at here. These two are orthogonal component of this vector. Am I right? You know orthogonal resolution of a vector. Am I right? Ax into x cap, ay into y cap. Now you can think like this is a kind of door. You can think like this a kind of door. You can rotate like this one. This plane. Okay. This plane. So can I draw this plane like this? This one. This is a plane. Can you imagine this plane? Speak out. So that you can just rotate this one. Now, so this is a vector I mean, this is one vector, this is another vector, which are again perpendicular to each other. Check this out. Just like this, isn't it? One vector here, other vector here. One vector here, other vector here. Is that okay? Now, again, if you add these two, you will get a resultant. This is a parallelogram law of addition. Actually. So this is also your parallelogram law of addition. Ax x cap ay y cap, and ax x cap ay y cap. This one is added to this one according to parallelogram law of addition. You are getting resultant vector. Or you can say this vector is resolved like this. Is that okay? Can you imagine this one? I need this three-dimensional imagination. Okay, it is required. So many cases. Okay. We call this one as a component form of a vector. Okay. So why we do this one? It is very easy to work with a component actually. Add a vector, subtract a vector, or taking a dot product, taking the cross product. Those are very easy. Okay. In this case. And we say in this case usually vector A is represented by its component. Am I right? Ax, Ay, Az, isn't it? So why? Look at here. If you have defined another vector like this, bx into x cap plus by into y cap plus bz into z cap, okay, then you can say vector b is represented by bx, by, bz. Okay, these are actually projection length. Can I say like this? These are projection length. These are projection vectors actually. These are actually projection lengths, am I right? Ax, Ay, Az. Or we say projection, am I right? What would we say? Ax, Ay, Az. Components actually. You say these are components of a vector, am I right? Components of a vector. Now, if you add A and B, what would you get? A plus B, isn't it? You can just write like this: Ax plus Bx into x cap. You can take x cap outside after adding, isn't it? Ay plus by, y cap plus az plus bz into z cap. Am I right? And this is represented by, look at here, this ax plus bx, comma ay plus by, comma az plus bz, isn't it? So that's why when you add a vector, components are getting added, isn't it? That's why it is very, what you call, easy to work with the components actually. To add vector, add its components, isn't it? To subtract vector, subtract its component, isn't it? That's how you can deal actually. Suppose if you want to multiply a vector by a scalar, okay? Suppose if you want to multiply vector by a scalar, okay, a into a, okay, then each of these components are multiplied with that scalar a into ax into x cap, like this, so that it can be written like this: a into ax, comma a into ay, comma a into az, isn't it? Very simple. Is that okay? Now, one more thing you need to observe here, these are perpendicular to each other. X cap dot x cap. What is x cap dot x cap? That's equal to mod x into cos 0. That's equal to 1. Am I right? Y cap dot y cap is equal to 1. Z cap dot z cap is equal to 1. Am I right? X cap dot y cap is equal to 0. They are perpendicular. Am I right? Y cap dot z cap is equal to 0. Z cap dot x cap is equal to 0, isn't it? So that's why you can take dot product between a and b. Suppose a and b are defined like this, okay? Can you see this one? A is defined like this, b is defined like this, okay? So a dot b, if you just work out this one, okay? If you just work out this one using this idea, okay? Using this one. So what will happen? Only x cap dot x cap part will remain. Y cap dot y cap part will remain. Z cap dot z cap part will remain. And that dot product equal to 1, so that this will be very simple: ax into bx plus ay into by plus az into bz. Isn't it? To find the dot product, okay, you just multiply individual component and then add, isn't it? That's a kind of rule you can generate here. And if you want to take dot product with itself, you can see here A dot A, isn't it? If you want to find dot product with itself, what you do? Again, speak out. Dot product with itself, ax square plus ay square plus az square, isn't it? Or again, you can write dot product with itself as a square, isn't it? So that you can write a is equal to root of ax square plus ay square plus az square, isn't it? We can generate this idea. I hope you have already done these things. Make it very brief, okay? Now one more thing is x cap cross y cap, okay? Look at it. This coordinate should be drawn like this only. This x cap cross y cap should be equal to z cap actually. Is that okay? X cap cross y cap, x cap cross y cap, z cap. Is that okay? Y cap cross z cap, that should be equal to x cap. Okay? How do you draw? Y cap cross y cap. Again, I feel more better with a scribble rule. Y cap cross z cap, that is x cap. Is that okay? Or y cap. How do I draw? Yeah, y cap cross z cap, x cap actually. But to show three dimension, I have drawn slightly like this, isn't it? Y cap cross z cap, x cap, isn't it? Similarly, z cap cross x cap is equal to y cap. Okay, the coordinate should be drawn so that it will follow this one. Okay. Be careful. If this is x-axis, this is y-axis, this is z-axis, okay? If you draw y-axis here, if you draw x-axis here, you have to draw z-axis like this. Is that okay? So that x cap cross y cap, okay? X cap cross y cap should be equal to z cap. Is that okay? And again, you can say x cap cross x cap is equal to 0, y cap cross y cap equal to 0. You can write these things, isn't it? That's not a big deal. Now, you can write A cross B. That means A is written like this, okay? A is equal to AX x cap plus AY y cap plus AZ z cap, okay? B is written like this. BX x cap plus BY y cap plus BZ z cap. Then you can write A cross B. You just work it out. Okay, you can write that one in a, what you call, determinant. X cap, y cap, z cap, okay? AX, AY, AZ, BX, BY, BZ. I hope you know this one also, isn't it? That means x cap into AY, BZ minus AZ, BY, isn't it? Minus y cap into AX, BZ minus AZ, BX plus z cap into AX, BY minus AY, BX. Okay, I hope you know how to take the determinant. Okay, it's a vector. Okay. I mean, using this one and using your article distributive property, you have to do that one, isn't it? A is written as addition of these three vectors. B is written as addition of these three vectors. You have to take a cross product. Then you have to work out. You can convert the last relation into a determinant actually. Okay. Now, obviously, you can see whenever you change any rows or column, isn't it? Suppose let me change rows here, your determinant sign will change. Am I right? Look at here, A cross B is equal to minus B cross A. That kind of property is there within the determinant actually, isn't it? Okay. If you want to write B cross A, then what you have to do? You have to exchange these two rows, isn't it? This is A cross B. If you want to write B cross A, just exchange these two, okay? It should be in that order, okay? A cross B, component of this should be in here, components of this should be here, okay? Be careful. Is that okay? Now, whenever you define a coordinate system like this, okay? Now, I have 2 points here, suppose, okay? I have one point x1, y1, z1, okay? I have another point x2, y2, z2. Is that okay? I have 2 points, okay, in space. Now, how do you draw a vector which is running from first point to second point? Let me call it as vector A. How do you draw this vector? Speak out. How do you write that vector? You know what is the coordinate of its tail? What's the coordinate of the head of the vector? Then how do you write a vector? Can anyone quickly tell me?
It's in a divided in, right?
x2 minus x1 into x cap, okay, plus y2 minus y1 into y cap, plus z2 minus z1 into z cap. Okay, I hope you know this fact. That's required. Okay. Now, if you define two vectors, okay, if you define two vectors in this coordinate, like ax into x cap plus ay into y cap plus az into z cap, okay, so bx into x cap plus by into y cap plus bz into z cap, okay, if you define two vectors, okay, now you can write you can find, if you know these, what you call these components, okay, you can find the angle between them using dot product. Because you can write A dot B. How do you write A dot B? I hope you have noted down this one. Okay, in that case, look at here. You can write A dot B is equal to AB cos theta. Am I right? What is cos theta? It's equal to A dot B. What is A dot B? AX BX plus AY BY plus AZ BZ. Am I right? Divided by A into B, am I right? Cos theta. What is A? A is nothing but root of AX square, AY square plus AZ square. What is B? Root of BX square plus BY square plus BZ square. Like that you can find the angle. Suppose if you know the components of a vector, you can find the angle between them, okay? So there is one problem. Let me upload that problem after this class, okay? Solve that one. Finding the angle between the vectors, okay? First define the vector properly in the component form, okay? Then try to find the angle between them. And there is one more problem, finding the, what you call, finding a unit vector perpendicular to one plane. I think I did ask this question whenever I called you, isn't it? While taking you to the batch, isn't it? How to find the angle between the vector, how to find the perpendicular to the plane if you know the two vectors in a plane, like that, isn't it? Yes, a similar problem is there. Just try to do that, okay? And one more small thing here. Scalar triple product. Let me not go for much detail, okay? A dot B cross C. A dot B cross C. We call this a scalar triple product, okay? Actually, this is equal to, actually, look at here. You have to change, you can change A, B, C in a cyclic order. So change A to B. So take A to B, take B to C, take C to A, okay? C dot A goes to B, B goes to C, A cross B. These two are equal. Again, so change them in a cyclic order. C goes to A, C goes to position of A goes to position of B, B goes to position of C. B dot C goes to A, am I right? C cross A goes to B. A. We call this a scalar triple product. All three are equal. Is that okay? Now this can be written as, look at here, if you know their component, okay, if you know the vector in a component form, this A dot B cross C, okay, that can be written as AX AY AZ, okay, BX BY BZ, CX CY CZ. Is that okay? Now look at here. Value of this one will become a determinant, am I right? Then determinant property will become property of this one. Suppose if you change B and C, change any to row, it will change the sign, isn't it? B cross is negative of C cross B, isn't it? Like that, okay? So now what you did here, you changed two rows or two rows here. From here to here, you changed two rows successively. Okay? So that's why again determinant value remains same actually, isn't it? You have done two changes here. From here to here, you have done two changes here, okay? So find out, again, determinant property will be followed by this scalar triple product, okay? If you know the vector in a component form, you can write that one as a determinant like this. And one more thing is, what is the geometrical significance of this one, isn't it? Magnitude of A dot B cross C. What is this one? Anyone quickly? Yeah, this is equal to volume of the parallel, just similar to A cross B magnitude, am I right? That was the area of the parallelogram, am I right? Similar to that one, this magnitude of the scalar triple product, that is equal to volume of the parallelepiped formed by these three vectors actually. So that means you suppose, let me take it like this. Suppose you have one vector here, you have other vector here, you have third vector here. Is that okay? A here, B here, C here, okay? So you can form a parallelepiped using them actually. You can form a parallelepiped using them, okay? And magnitude of the scalar triple product, that's equal to volume of the parallelepiped, or let me draw it like this. Suppose if you are worried, this is a nice way to draw. Is that okay? So let me take, this is vector A, this is vector B, this is vector C. Is that okay? So this is equal to volume of the parallelepiped which is generated by ABC. Can I say like this? This is a parallelepiped generated by ABC. Is that okay? And that's equal to what? This magnitude is, again, sometimes it may be negative, okay? You have to take mod, okay? So modulus of this one is equal to volume of the parallelepiped What is the spelling of parallelepiped?
Parallelo, P-A-R-R-E-L-O, P-A-P,
P-A?
R-R,
Hmm. Hmm.
Parallelo.
Whatever, okay? Volume of the parallelepiped generated by A, B and C. Look at here. This scalar triple product is a test, okay? Scalar triple product is a test of, okay, whether vectors are coplanar or not. Look at here. If A vector is here, B vector is here, if C vector is on the plane of ABC, let me take a plane, okay? Let me take a plane. Is that okay? If all A, B, and C are on the same plane, then it will not generate any volume at all, isn't it? it will not generate any parallelepiped at all, isn't it? What is the volume of the parallelepiped here if all are coplanar? 0. That's why if scalar triple product is 0, that means these vectors are coplanar. So can you note this down? If scalar triple product is 0, vectors are coplanar. Okay? If scalar triple product is non-zero, vectors are non-coplanar. Okay? That's why scalar triple product is a test of whether vectors are coplanar or not. Okay? And we have seen this one in case of linear dependency and independency, am I right? In case of linear vector space, isn't it? We have seen again, if they are coplanar, they are linearly dependent, am I right? If they are non-coplanar, they are linearly independent, isn't it? You can combine A and B to form C, isn't it? If they are coplanar. But if they are non-coplanar, if you linearly combine A and B, you will not generate C, isn't it? So it's a test of whether vectors are linearly dependent or independent, okay? Now look at here. We have a vector product here, A cross B cross C. B cross C is a vector. If you take cross product with A, that's also a vector, okay? So now you can simplify that one by one rule. We call it as back cab rule. Back cab rule, okay? So B into A dot C, back, can you read like this? A dot C is a scalar multiplied with a vector, total is a vector. Minus, okay, minus back cab C A dot B. We call this one as back cab rule, okay? Back cab rule. Again, A dot B is a scalar multiplied with a vector. So total is a vector, okay? You may need this one. You may need some more rule, okay? Again, later, okay? In the later part, then we shall just take it whenever we need, okay? Is that okay? Speak out. Vector triple product. And one more small idea here, okay? One more small idea before closing. I will follow the notations, whatever given in the Griffiths, okay? So that you can solve Griffiths problem easily.
What the physical significance of this cross product?
I told you, unless you assign some physical quantity, don't talk about physical significance. You can only talk about geometrical significance. Isn't it? Yeah. Look at here. These are abstract things, am I right? Whatever we have discussed, these are abstract things. If you say A is something, B is something, C is something, okay, A is some electric field, B is some magnetic field or something, then you can talk about physical significance of this triple product and all, okay? We shall see that one. Somewhere we use this, this triple product, okay? Somewhere later. So that's why, so differentiate this pure math with modeling, okay? In the modeling part, again, we can give all physical significance. You can't give physical significance here. You can give sometimes geometrical significance. Just like geometrically, modulus of that scalar triple product, that's equal to volume of the parallelepiped, isn't it? Modulus of A cross B, that's equal to volume, area of the parallelogram, isn't it? Like that, okay? Now look at here. Since I am following Griffiths notation, okay? Because again, so that soon after the class you can solve the problem from Griffiths, okay? But you should try to read different textbooks so that whatever you grab, okay, that should be independent of the notation. If it is so dependent on notation, then that is not complete, okay? Try to read one more textbook along with Griffiths electrodynamics so that you should be able to think independent of the notation. But while discussion of the theory, throughout that one, I am going to follow Griffiths notation, okay? So that soon after the class, you can quickly solve the problem. But sometimes you may encounter the problem, okay, which contain different notation. Or you convert that notation into Griffiths notation and solve that one. That's one idea.
In exam hall, in exam papers,
They are strictly following Griffiths notation. Actually, very nice notations actually. We shall follow the same notation, okay? So throughout our discussion, okay? So now again, whenever we choose origin, usually we choose origin, okay? Again, in any problem, we choose origin somewhere. We don't use any vectors without using any origin. Is that okay? We choose origin. I call it as O. Okay? X, Y, Z, O. Is that okay? So you have some point here, okay? From origin to some point, we call this as position vector. Am I right? I hope you know that one. Am I right? Position vector. I call this point as X, Y, Z. Okay? This is a position vector. What is the position vector? It's a vector from origin to the point in a space, isn't it? That's a position vector. So again, you can write this vector, am I right? R vector. How do you write? X into X cap plus Y into Y cap plus Z into Z cap. That's how you write. So its direction is here R cap. Away from the origin, isn't it? I hope you know this one. And how do you write this, what you call magnitude of R? Speak out. That's equal to root of R dot R, isn't it? That is X square plus Y square plus Z square. We call this as position vector of a point P. I hope you know this one. Okay? Position vector. Is that okay? Now, occasionally, okay? Not occasionally, frequently, very frequently, okay? We will choose origin somewhere here, okay? We will choose origin. And we will have a source charges. Source means that can be current carrying wire. Source can be charges. Charges will produce electric field. Current carrying wires will produce magnetic field. You know that one, isn't it? So we will have a sources usually, okay? So sources here, okay? We call this as source point. I call this as source point. Okay? Very frequently we use this notation, okay? Source point. From origin to that source point, okay? The vector from origin to this source point, okay, we call it as R prime vector, okay? That source point, that can be point on a charge, okay? That can be point on a charge distribution, which is generating field, okay? That can be point on a current carrying wire, which are the source of fields. Can I say like this? So now this source point is usually written as R prime vector from origin to source point. Is that okay? That is written as R prime vector. At that source point, this point is written as X prime, Y prime, Z prime. Is that okay? Notation, okay? I'm talking about notation. Is that okay? Suppose here you are finding field. That means either magnetic field. If it is current carrying wire, it's a point on current carrying wire, magnetic field. If it is some source point is some charge or something, okay? So then electric field like that. We call this as field point. Field point. Okay? From origin to this field point, okay? From origin to field point, that is written as R vector, just like this position vector. And this field point is noted like X, Y, Z. Okay? X, Y, Z. Field point. Source point X prime, Y prime, Z prime. Okay? Almost in all cases, okay? Almost in all cases. Look at here. This is the origin which is our choice, isn't it? So that's why field point at field point, okay? That is usually depends on how far it is from source point, not on this origin, isn't it? That's why we need one more vector from here to here, from source point to field point. Actually, our field or force or whatever you define here, that depends on this one, because you can change origin, am I right? If you change origin, R prime will change, R will change, am I right? But field should depend on source, isn't it? That's why we need to draw a vector here. We call it one as source to field point, italic R vector. Is that okay? Can you write what is that italic R vector? Italic R vector is equal to R vector minus R prime vector. Check this out, speak out quickly. R vector minus R prime vector, okay? You can choose your X, Y, Z here. Okay. Now you can change this origin. Okay. Then R and R prime changes, but this italic R will not change. Look at there, isn't it? So these are the notation we are going to use. Is that okay? Now can you find R cap? Many times you may need to define. How do you define this R vector? You know this one, am I right? You can define R prime vector. R prime vector is equal to X prime into X cap plus Y prime into Y cap plus Z prime into Z cap. Am I right? R vector is equal to X into X cap plus Y into Y cap plus Z into Z cap, isn't it? Can you write this one? R vector minus R prime vector is equal to X minus X prime, isn't it? Into X cap plus Y minus Y prime into Y cap plus Z minus Z prime into Z cap, isn't it? I hope you can write these things. Is that okay? Define that R cap, unit vector from source to field point, okay? R cap, how do you write? R vector divided by magnitude of R vector, isn't it? X minus X prime, X cap plus Y minus Y prime, Y cap plus Z minus Z prime, Z cap whole divided by root of X minus X prime whole square. You can write like this, isn't it? Where this is the magnitude. We use these things, okay? And one more thing that I need to define here, okay? I don't think I need this one right now, okay? Later I need this one. We are going to define a displacement vector, infinitely small displacement vector. If you have R here, okay, I'm going to displace infinitely small from this point to some other point, some neighboring. I'll call that one as DL vector. Is that okay? That DL vector is written like, look at here. How did you define R vector? X into X cap plus Y into Y cap plus Z into Z cap. Am I right? So if you displace from that point, you are changing X, Y, Z. You are not changing X cap, Y cap, Z cap. X cap, Y cap, Z cap are not changing in Cartesian coordinate. Okay, they are fixed. Okay, once you fix that one, if you go to neighboring point, this DL vector is written like this: dx into X cap plus dy into Y cap plus dz into Z cap. We may need this one, okay, many cases. Let me define this again, okay, later. You can say that's a distance between R of X comma Y comma Z to R of X plus dx, or this is a displacement vector from this point to this point, X plus dx, Y plus dy, Z plus dz, okay. Try to grab this small method. Infinitesimal displacement vector. Infinitesimal displacement vector. This length is infinitely small, okay, very, very small. It's a kind of derivative. Again, we use this one in case of derivative integral, okay. Yeah, the whole electrodynamics understanding that depends on how much hold you get on vector algebra and vector calculus usually, okay. Yeah, that's why I'm spending very considerable time on vector calculus. If you are not understanding vector calculus, you will not understand the later part of the syllabus, okay. So that's why he mentioned particularly that vector analysis, okay, whole chapter, okay, one full chapter, okay. And 2 to 3 more small concept from mathematical concept is missing here, which are appearing in exam, that I will discuss separately, okay. Some directional derivative idea, tangent and normal, that can be discussed using gradient divergence and all, okay. That kind of ideas are missing, that let me discuss separately, okay. Yeah, for rest of all, I think the whole book is sufficient for our exam, okay. Yeah, any question?
Sir, that whole point is observation point.
Not like that. Not like
A
that.
reference point.
Reference point. You can say like that. I mean, to work out, you need coordinates. Am I right? To work out something, to work out the theory, you need coordinates. But if you go to lab, what you do? You find field here. You have source here. You find field here. God hasn't decided this one, isn't it? That is purely
So
our
we
choice.
can choose in the reference point that is the source point.
Anywhere. You can choose this one anywhere, reference point. And our whatever the result, whatever you get in lab, that doesn't depend on this reference point. This is purely our choice. Is that okay? But most of the case, we choose this reference point so that our mathematics is simple. Okay, we don't make it mathematics lengthy. Okay, we choose this reference point so that our mathematics is simple. Some symmetrically, we situate this one symmetrically. Is that okay? Speak up.
So there are two observers, right?
No, there are not two observers. I am saying this is source point. Charges or something. This is a field point. Charges will create field. Again, current carrying wire will create magnetic field. You know that one? It's a source point. This is a field point. Where is observer?
No, I am saying.
No, again.
If I will sit in the source point, and I can observe that origin. If
If you go to lab, you will not find XYZ coordinate anywhere. Isn't it? You keep some charges in the field point. You will try to find what is the force on it. Isn't it? This is purely bookkeeping. It is to work out the theory. Is that okay? Speak out. Where will you find XYZ in lab, isn't it?
No, if I will do some
You have source point, you have field point. In the field point, you are going to place the charge and you are going to find what is the force on that one and all. That's only you can experience, okay? Ultimately, you have to convert that one into field and force. Ultimately, field, force, work, energy, that is the ultimate values, okay? These are bookkeeping terms. Is that okay? Speak out. And don't make it, don't situate this one so that our mathematics is lengthy, okay? Situate this one so that our mathematics is easy, okay? We shall see that. And this is very important concept, okay? Sometimes we may do integration with respect to this source point if there are many sources, okay? Sometimes we may do integration with respect to this field point. Then we write dx, dy, dz. Sometimes we write dx prime, dy prime, dz prime, okay? Those are very, very important concepts mathematically, okay? We shall see that.